Hiya. So in this video, we're going to look at an example of all of these theorems that we kind of used to kind of see where this kind of takes us. So let's first start off with an example. And basically, we're going to talk about something called random walks. So this is super heavy in physics. So this actually started as a physics example. And so we're just going to kind of play around with that. And so what we do is we have an infinite line of slots. So I have kind of spots that people can stand, and it's infinitely long. And I put a particle in the middle. Just choose wherever the middle is. It doesn't really matter. Just find a middle. It's infinite line, so there's technically no middle. But anyway, put a middle. And we know every second the particle moves left with probability P of L. It moves right with probability P of R. Or it stays where it is with probability P of S. So this is why this is called a random walk, because you start somewhere and every second it kind of moves. So it's like randomly walking in some kind of random way. But notice how we have to specify that P of L plus P of R plus P of S has to equal to 1. Because at every moment something has to happen. Either you stay put, you go left, or you go right? And so what we're going to do is we're going to put in numbers and kind of see what happens. The particle's having a lazy day, so it's going to stay put half the time. And it's going to move right or left with equal probability 1/4. And that's it. So let's see. We're looking at roughly 86,400 seconds in a day. So what we'll do is we will calculate 88,200 seconds, because this will make numbers easier. You'll see later on why. And we're going to ask the chance that the probability is 300 slots away to the right from where it began. So let's kind of visualize this. So here I have my slots. Here is my 0. So this is where my ball kind of starts, or my particle. And I want to know 300 to the right. So let's kind of figure this out a little bit at a time. What I can do is I can let xi, so every trial, so every second will be the ith thing. And we'll let this be equal to, so if it moves to the right, we'll add 1. Plus 1 if right. 0 if stays where it is. And we'll do -1 if left. And the reason we're going to do this is because now if I sum these up, S of, I guess, 88,200 is basically going to tell me, so this is just the sum of the xi. Oops, big X. This is going to tell me how far the right, left I've moved, right? I just sum them up, and then if I'm at 400, then I know I've moved 400 to the right at the end of all this. If I'm at negative 212, then I know I've moved to the left 212 spaces. So this is just going to keep track of everything. And these are things that you kind of have to think about of how do I write these things out, right? This is kind of the big problem that we've started from the very beginning. How do I write this out? So first we're going to want to calculate the expected value of any one of these. It's always the same distribution. They're all independent. So let's see the expected value of one of these trials. So here I'll write that this is equal to xi, so we can be extra prudent. And here we just take the sum of x, probability that x is equal to x. And here x is basically either -1, 0, or 1. So x is equal to -1, 0, or 1. So we have -1 times, here left, the probability is 1/4. So here I'll add, this is left. And then we need to add stay put. So this is stay. And then we need to add 1 for moving to the right. So this is right. And notice how I kind of did things so everything cancels. So this part is 0, minus 1/4 plus 1/4 is equal to 0. So our expected value is to stay. Like I said, it's a lazy day. We just stay in where we are. Our expected value is to not move, well, over time. So what is x squared, right? What is this equal to? This is almost the same, except we're squaring everything. And in this case, things do change, right? Because we get minus 1 squared over 1/4 plus 0 over 1/2 plus 1 over 1/4. So I actually get 1/4 plus 1/4, which is 1/2. So what this means is the variance is x squared minus e of x squared. So I get 1/2 minus 0 squared, so it's 1/2. It's positive, so we know we did things right. Well, probably right. And then SD of x is just the square root of variance. So it's the square root of 1 over 2, which is just 0.7071 dot 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 dot. Okay, so what are we asking? So we calculated everything just to be safe, because we know we're probably going to use it. And we're asking what's the probability that we move 300 slots away to the right. So remember, we can kind of do this through our summation. So really what we're asking is what's the probability that S of 22,800, 88,200, I did this backwards, 88,200 is greater than 300, right? This is kind of what we're asking. So let's kind of calculate the expected value for our S, right? So what is the expected value of S of 88,200? This, from the square root law, we have 88,200 times e of x, which is just 0, right? So this is square root. And this part is equal to 0. So something times 0 is just 0. So kind of nice and easy, eh? And then we have, let's figure out the standard deviation. 88,200. This is the square root of, well, we had 88,200 times 1/2, right? Because what we end up having is, well, okay, we'll do n, right? So this is, again, square root law times 1/2, not 1/2, sorry, times the square root of 1/2. And this, we'll see, is just 44,100. And this is why I chose 88,200, is because when we do this, we get 210. So a nice round number. So 210. So now let's figure out what this is. And so is 300 slots away. I guess I should have said, sorry, is more than. So this is bad writing on my end. More than 300 slots away. So what we want to calculate is this, actually. It's 300 more. 300 slots. No, go away. Oh, it's already gone. There's 300 or more. Or is at least? At least, that's better. Is at least. 300 slots away. And so what we want is this formula here. So let's kind of calculate that. I have room. Yeah, I have room here. So let's calculate this. 300 is less than S 88,200. And at this point, this should look similar, right? So the thing is, we're going to go back and look at our central limit theorem. And notice how the central limit theorem has a and b, but we have to do the expected value and the standard deviation, right? And so what we need is we need to actually take this and we need to standardize it. So I need to do 300. So let's see what we need to do. I do need S 88,200. Was it minus? I think it's minus. Yeah, minus the expected value of Sn. So here I should do it minus E of Sn. And then I need to divide by the standard deviation of Sn. So this is going to give me, so 300 minus E of Sn, this is just 0. So this is 0, and 210 for the bottom one. So we have 300 minus 0 divided by 210 is less than or equal to our thingy. So in other words, this is, and then I guess this is less than or equal to infinity. So here we have 1 minus, so this is our approximation from the central limit theorem. Uh, 300 over 210. So here, if we just plug this in, we get 1 minus phi of 1.4286, which is 1 minus 0.9236, which is 0.0764. So there's a 7.64% chance that I'll be super far off to the right. Which is not 0, right? Like it's still a fairly big chance, as long as I plugged in these numbers correctly. But yeah, so it's pretty nice. It's pretty neat. And the big reason for this is because we've done a lot of numbers, right? We've done 88,000. So we'll stop this video here. It's already super long. And in the next video, or potentially two, no, just one video. In the next video, we'll look at, since we did normal approximation, we'll look at skewness and kind of how this plays into the wider picture of everything. So I will see you in our next and last video. So see you then.